This is Keith and Brian doing our neuron assignment. So we have our circuit here to represent the neuron, which has three kind of key sections. So there's the gating channel with the sodium gate and the potassium gate. There's a low pass filter type design which controls the potassium channel, and there's a bandpass filter which controls the sodium channel. So I'm going to start off by talking about this this kind of modified C4 bandpass filter. So as we saw in the previous assignment, the bandpass filter acts here so that when there's a step response, the output rapidly drops based on your biasing currents. So the biasing currents of the OTA affect the time constant. So by tuning them appropriately, you can keep the time constant small so that the C4 bandpass has a fast response to the step current. So the way that this works, when the input, the VMEM, spikes, the negative terminal of this top OTA, the voltage there will increase as well. There's a delayed effect due to the capacitor, which is just off screen here. As this negative terminal voltage increases towards Vref, the output of this OTA decreases. So the gate voltage of the PFET decreases, and this creates the sodium channel here. And what that, the effect of that is that VMEM increases towards ENA, the sodium voltage here. Once this output here decreases, the feedback loop causes the negative terminal voltage to return to its previous value.
So here's the second half of the circuit, which just acts as a low pass filter. So for a large increase in VMEM, we will see a slower change at CK. So this is the circuit from the previous lab, the low pass filter. So we just expect to see something similar here with the low pass filter. So as the frequency goes higher, our gain gets lower. So the value of change in this lab was our bias current for the OTA in the low pass filter half of our neuron circuit. So in the previous lab, we saw that as we change this bias current from high to low, the response was slower for a lower bias current. And here's an example from the previous lab where the OTA lagged behind the step response because it was acting as a low pass filter.
So when we put all of that together, as we have an input step function which initially causes the PFET to conduct, we get essentially no voltage drop across the PFET because it's conducting like the sodium channel, and that means that VMEM here effectively spikes up towards the value of ENA. Then after that, the effective low pass filter kicks in, so that causes the potassium channel to turn on and conduct, and because it has much higher conductance as an NFET than the PFET did, the voltage drop across the NFET is much smaller than that across the PFET. So what that does is that drags VMEM down towards the value of EK. So that returns Vmem back to its resting value. And so once we've seen Vmem spike once, that acts as the next kind of input step for the circuit. And so we just see the same behavior repeated, whereby one spike induces the next spike, and we get a continuous spiking output pattern.
So as we increase the bias current in the low-pass filter of our circuit, it makes the response of it faster. So that's why we see the difference in the speed of the spikes. As we increase the bias current, we see a higher frequency in spikes. So for a bias current of 10 nanoamps, we saw 20 spikes. For 1, we saw 15 spikes. And for 0.001, we saw 10 spikes. And this was over a 10-second window. Based on our notes from class, this sort of resembles the square root behavior, where as we increase I, we'd get like square root number of spikes increase. It's not perfect, but it is close to that behavior.